So we've seen how to use the metric equation to solve certain types of problems in special relativity. And in particular, we just used it to analyze a muon experiment, the results of which give very, very strong evidence that the special relativistic view of time as being not absolute is correct. What we'll do for the rest of this unit is to step back a little and try to think about what does the metric equation mean. We've seen how to use it, but what does it mean? What is it telling us? And in particular, what's that minus sign doing there? So delta s squared is delta t squared minus delta x squared. And that minus just looks weird, right? You want it to be like the Pythagorean theorem, but there's a minus there instead of a plus. Okay, fine. We use that for analyzing problems. Seemed okay. But what does that really mean? And is there a way that we can picture all of this geometrically? So that's what we're going to talk about in the next couple of videos. So what that minus sign means is that space-time is not flat. It's not Euclidean. So I'll explain that in a number of different ways. But first, let's go back to thinking about regular maps. So here's a regular map. It's a map of North America. So I've got US, Canada, Greenland. I printed this off of Google Maps. And so this is a nice flat map. But as you no doubt are aware, it turns out that the world is actually not flat. The Earth is round, right? Round like this lacrosse ball. And so what happens when we try to take a spherical surface and turn it into a flat map, that areas get stretched. And you're used to this most likely. On a lot of map projections, Greenland looks gigantic, but it's not really, right? Greenland isn't really bigger than the US, even though it kind of looks like it on this map. So literal distances on this map don't correspond to actual distances because the space that this is representing, even though this is a flat sheet, is not really flat. So let's explore that idea a little bit more, and then we'll explore the same idea, but in the context of space-time instead of just space. So here's a map, a flat map of the round Earth. And as we know, distances on this map can be deceiving. So using Google Maps, I measured a couple distances. One distance I measured was from here to here. And that turns out to be right around 720 kilometers. And then I measured a distance down here in the northern part of the US. And from here to here, from the MT for Montana to the NM for Minnesota, or MN, sorry, which I've since covered with dots. This distance is also 720 kilometers. And that's because this flat map of the round Earth does not faithfully represent distance. So the literal distance on this map cannot be inferred to be the literal distance on the surface of the Earth. And I mean, it's pretty clear that this blue line is longer than this red line, even though they're supposed to represent the same length, right? So I could get a ruler out. This is almost 6.5 centimeters, and that's supposed to be 720. And this is like 2.33 centimeters, and that's also 720. So we're used to this idea that on a map, a flat map of a curved surface, the distance on the map is not a faithful representation of the distance that is being represented underneath. So let's explore a similar idea, but on a space-time diagram. So we've talked about spatial distances on a map. Let's now talk about how to think about the space-time interval on a space-time diagram. So as a reminder, here's the space-time interval, delta s squared, that's the space-time interval. is delta t squared minus delta x squared. So let's look at the space-time interval between a couple of different points. So let's do the origin and this point here. So between A and B, the delta t, I can just read that off the graph, that's 5. So delta t is 5 seconds. Delta x is 0. They have the same x coordinate. Delta x is 0. X doesn't change from A to B. So I can plug in here to find delta s. And let's do that. Delta s squared is delta t squared minus delta x squared. Delta s squared is delta t squared, 5 seconds squared. And delta x is 0. So delta s squared is 5 seconds squared. So delta s is 5. Just take the square root of both sides. So delta s, and maybe I'll just say BA to indicate between A and B, is 5 seconds. Okay, let's look at another pair of points. And I will choose, let's choose this point. I'm going to call that C. And let's look at the value for the space-time interval between event A and event C. So we do the same thing. We can read delta t and delta x right off the space-time diagram and then use this formula to find delta s. So let's do that. Delta t, well, that's 3 seconds. That's the difference in time between event A and event C. 1, 2, 3. All right. Delta t is 3 seconds. What about delta x? So the difference in the x coordinate from event A to event C is 1, 2, is 3 seconds. All right. So, no big deal. This event C just happens to happen 3 seconds later in space and 3 seconds later in time. Okay, let's figure out the space-time interval using the metric equation. So I'm going to plug in delta t and delta x. Maybe you can see what's about to happen, even though my hand is blocking the formula. 3 squared minus 3 squared, that's 0. So delta s, CA, between these 2 points, is 0. All right, so what is this telling us? So this is telling us that the space-time interval, which is important, it's this thing that's deeply real, that all, it's a time interval that's agreed on in all inertial reference frames, that it's not something that we can read directly or interpret as a distance on a space-time diagram. And okay, that's a little bit weird, but really we're actually used to that because even on a map, a flat map of a curved surface, we know that we can't interpret distance, the distance on the map, as the true distance that's being represented, the thing that's deeply real. All right, so where does this leave us? Is there anything we can do, any geometrical way we can make sense of delta s squared, a way we can start to see what delta s might be, the time space-time interval would be in a map? The answer is yes, and we'll start exploring that in the next video.